Now, this is the way the bond stress expression that is has been given in the transfer length. So, this is for flexion. So, we have understood now what is the bond that is created during the transfer length or in the transmission length, and the bond that is has to be developed to take care of the change in your bending moment. Okay. Now, let us find out the expression for your average bond stress that is developed in the transmission length, right. So, the Marshall again in 1960s, you can see that this is almost 1950s, they did a lot of testing and then they proposed this very simplified expression between the bond stress and the distance. So, you can see here it varies very quickly and then it is basically dying down like this, right. So, this is the expression. So, at any distance x from this end, the bond stress at a distance x is going to be the maximum bond stress multiplied by e to the power of minus 4 into psi into x by diameter. Now, what is psi and what is x? Psi is nothing but a constant which is defined as the ratio of change in bond stress to steel stress, right. So, if you know your bending moment diagram, you know how the steel stress is going to change. So, and x is the distance from the free end where we are trying to calculate what would be the bond stress, right, and phi is the diameter of the wire or strand, and FSC is the effective stress in the steel at the end of the transfer zone. So, somehow we have to bring in that initial stress and effective stress in the pre-stressing steel as well. Now, in that expression you will show that we will also need to include the M factor, the bending moment that will be developed due to the internal forces as well. So, this is the expression for your bond stress at any distance x from the free end as a function of your maximum shear stress and the other parameters like the diameter of the pre-stressing strand and psi, which is the constant which defines how the ratio of bond stress is going to change as a function of your steel stress, and x is the distance of the section from the free end and so on, right. Similarly, the expression for is also given. The stress in the steel at any distance x can be given as a function of your effective stress times 1 minus e to the power of minus 4 psi x by phi. Okay. So, this way we can calculate your parameters. Okay. Now, so this is what we said. So, this is for bond stress expression what is developed in the transfer length. Now, what is the development length? Development length, as we have explained previously, it is a summation of your transmission length plus the bond length, and again we have discussed. So, this is the thing. So, you see here this is the distance that is required to develop your effective pre-stressing force. Now, at ultimate again I have to develop some additional stress in the pre-stressing steel that we are going to call that as LB. So, the total development length is summation of your transmission length plus the bond length, right. So, this is what we said. Initially we develop the stress FP effective, and again you see the stress in the pre-stressing steel will be quite high compared to the reinforcing steel, right, because the initial stretching itself we are going to put like 75% of your ultimate strength. So, because of the load effect, or in other words what I am trying to say here is the difference between the F ultimate and F effective is not going to be that very high, okay, because this will be in the order of let us say 1300 megapascal. Here ultimate we may go up to some 1480 or maybe let us say 1500 megapascal. Okay. So, usually we take 0.87 times FP, okay, 0.87 into 1860, so roughly about 1600 or so, okay, let us say 1600. So, is only that 300 megapascal range is the incremental stress that it is going to come because of the load effect, because why? The initial stress itself is quite high in pre-stressing steel, unlike in reinforcing steel the stress will be 0, and then because at ultimate it can go up to 0.87 times Fi. Here you cannot go. So, effective stress itself what you have locked in is initially is high. So, because of the load you can go only moderately slightly higher value as per your code limits. Okay. Okay. Now, the development length. Now, let us look at what is the development length. considering only the bond length where the stress in the prestressing strand increases from effective prestressing stress to ultimate. So, I want to find out what is the expression for your bond length, right. So, at left end I have effective prestress multiplied by AP will give me the stress at the end of transmission length. Now, at ultimate this is going to be FP ultimate times AP, right. Now, the difference has to be developed as a bond stress at the interface of the prestressing steel. So, that is what we are doing. So, if you put the horizontal force equilibrium, FP effective times AP is the force in the steel on the left side, and on the right side I have FP ultimate times AP, that this is a lesser force that has to be added with a tau BD times AP. Maybe I should say, I should put this as AP. Okay. So, AP. Or let us say put AP. Okay. So, FP effective, so in this way I can find out an expression for your bond stress like this, FP ultimate minus FP effective times AP. Now, what is this in the area of the surface? So, that is the reason I think is given surface. Okay, I see the point. So, this is basically the surface area. Okay, it is not your tension steel, it is a surface area. So, pi into D times LB is your total surface area. Surface area multiplied by the bond stress tau BD will give me that force, that is the entire force that are developed at the interface, right. So, in this way we can find out an expression for my bond length as the difference between FP ultimate minus FP effective times diameter of the bar divided by 4 into tau BD. So, this is an expression for your bond length. Okay. So, now we have found out expressions for transmission length, found out expressions for your bond length due to flexure, then we can do the calculations, right. So, let us run one example problem. Okay. So, again very important to note that development length is summation of, again development length LD is summation of your transfer length plus bond length. Okay. This is from flexure loading, okay, and this is to develop FPE, okay, the length required to develop the effective prestress. Okay. So, these both of them together is what we call that as development length, okay, LD. Okay. This is very important. So, this is the expression of LB. Previously, we found an expression for your LT. So, let us run one example problem and then it will become very clear. Okay. So, a prestress beam, we have 200 mm wide by 400 mm deep, which is pre-tensioned by 5 numbers of high tensile wires of 7 mm diameter, and they are located at an eccentricity of 150 millimeter. Now, the maximum shear force is 450 kilonewton. If the modular ratio is 6, now we need to compute the bond stress, okay, developed assuming the section is uncracked and the section is cracked. Okay, we derived two expressions, right. So, let us use that now. Now, okay. So, what are the moment of inertia B dq by 12? So, you know how to calculate that, 2.1 into 10 to the power of 9. Now, distance of the tendons from the center of the section is 150 millimeter, as you can see from the cross section, eccentricity is given as 150 millimeter, right. So, if you go back and let us say we derived an uncracked section formula, if you remember, right. Tau B is modular ratio times the surface area AS times the distance of the fiber, the rebar, and then the shear acting in the cross section divided by I into the perimeter, right. Now, pi d is your perimeter of the surface. The surface area is pi by 4 into d square, which is the area of your steel, and times y is the distance. Okay. So, you can see we derived this, V is the shear that is acting in the section, which is 450 kilonewton, that is given to you in the problem, right. Now, modular ratio is 6, right. Now, the area you have 5 numbers of 7 diameter strands. So, if you simplify this, so you will find that it is only the diameter that will be there, which is 7. So, it is there, and then divided by modulus of ratio. So, basically you get this, and then you have 4. So, if you substitute this, basically you get your calculations as okay, basically see this pi d will get cancelled. So, you will get only with d and then only the diameter d, which is that is why we put this 7. Okay. So, 7 is your diameter. So, this is modular ratio, let us say alpha e, and this is your diameter, and this is your y, and this is your shear. Okay. So, if you simplify that, this is how you get, and your bond stress for an uncracked case as expected, it is going to be less, okay, which is 0.34 megapascal. Now, let us look at what happens for a cracked section. So, we derived this expression. So, if you see that the lever arm depth, we take that as 350 millimeter, and how do we get that lever arm depth? Again, if you go back, the formula is this. Okay. The bond stress for a cracked section will be the shear that is acting in the section divided by the lever arm times the perimeter per unit length, right. So, this is we are doing calculation stress. Okay. So, the shear is 450 is given to you. Now, what is the lever arm? The lever arm is what we are showing here. For a cracked condition, let us say we do it in a conservative way, we are looking at an ultimate condition. So, in an ultimate condition, my strain epsilon Cu at failure is 0.0035 as per IS 1343, and this we take that as 1240, okay, which is epsilon PE, right. So, if you substitute that and you find that it is going to be approximately it is equal to JD will be equal to 7/8 of your D. Okay. So, that is what your stress is. So, 1240 is nothing but your effective pre-stress, let us say that let us say that it is there. So, if you do that in simple calculations, your lever arm JD works out to be 7/8 of D. So, 7/8 of your D is what you are saying. So, this is how do we get this D like this? This is overall depth h by 2 plus the eccentricity is nothing but your effective depth, right. So, h by 2 is 500 by 2 and eccentricity is 150. So, if you substitute 7/8, that works out to be 750 millimeter. Now, the change in shear 450 divided by 350 times the perimeter will give me the shear stress, which is very high, 11.69 megapascal for this. Okay. So, this is the way we calculate your bond stress. Okay. One thing to note again, when the system is uncracked, you will have low stress, but when it is cracked, you can have a very high bond stress as well. So, that is why this is a local bond stress. Okay. Now, one more important thing we need to know is when you develop this pre-tensioning system, when you transfer the pre-stress, pre-stressing strands, as we have seen, it is going to regain their original shape and it is going to create this inclined compressive stress. Okay. That is what we said, because of that wedge action in the transmission length, you will develop some inclined compressive stresses through which only the bond is developed, right. In turn, if you look at it, there is always going to be a radial component in the radial direction, a transverse tensile stress will be developed. Okay. So, that is what it is going to be creating some tension, and we need to be very careful about it. Okay. So, Marshall and Mattock, they developed this empirical formula for determining the transverse tensile stress in this fashion. Some transverse tensile stress Fe is function of bending moment divided by Bw into d square. Now, what is a K? K is a constant that depends upon the slope and distribution of the tendons. Usually, it ranges between 9 to 18 depending upon your slope of the tendon profile you can find. So, basically this all comes from elastic stress analysis. Okay. So, let us look at it now. Again further, Marshall and Krishnamurthy, they developed this empirical formula, and how much is this maximum transverse tensile stress as a function of moment and the transfer length at any distance x. Okay. So, they gave an expression for any distance x that you take in the transmission length, how much will be the maximum transverse tensile stress. Okay. So, if you see, the maximum transverse stress will occur at the centroid of the end face, that means at x is equal to 0. So, if you put x is equal to 0, you will find that it is going to be 10 m divided by Bw into h into LT. So, this is how you find the expression for maximum transverse tensile stress, and more details are given in this particular paper, which is a very old classical paper. Now how do we tackle this transverse tensile stress? So, they found again as a distance, you can see that actual distribution for this transverse tensile stress is like this. Okay. So, your more tension will be there at the initial location, then it will die down. Okay. So, after the transmission length, the tensile stress will become actually 0, right, or near 0 I should say, right. So, the transverse tensile stress are higher at the end portion, just at the location where the pre-stressing steel has shrunk, and at that location you are going to have high transverse tensile stresses, and it is going to reduce gradually within this transmission length. And then Krishnamurthy, he proposed a linear approximation for this. If I can calculate my maximum transverse tensile stress, and he said that, let me say that at a transmission length, half of the transmission length, it is going to reach 0, right. So, with this profile, now we can calculate what is that transverse steel that we need to put to arrest this transverse tensile stresses. Okay. Okay. So, the reinforcement must be provided at the end region to resist the crack, because if the Fe max is high, it will basically create a splitting crack, along the horizontal line, right. So, we need to calculate. Now, some way we have to calculate how much will be the tension force. So, you can say that this, if you assume a linear distribution, so we see this Fb max by 2 into Lt by 2 into Bw will be that approximately the transverse tensile force. Then once we calculate my transverse tension force, that has to be resisted by the vertical stirrup reinforcement, and let us say if I put some area of the 2-legged or 4-legged or whatever it is, times the stress should be equal to this. Let us assume that if I am saying that ASV is, if we see that, if we can substitute that equation. Now, if we see this simplified expression, so we can find ASV as half of Fe max by Fs times Lt by 2 into Bw. This is one, we have found this one expression for the amount of transverse reinforcement. Right. Now, we also have expression for this Fp max. Previously, we have shown that Fp max can be expressed in terms of the moment which is acting about the horizontal plane, right. So, Fp max, you see at x is equal to 0. So, we found that Fp max is 10 m divided by Bwh into Lt. So, if I substitute that expression for Fp max in this equation 1, then I can find directly an expression for your transverse reinforcement as a function of moment that it is acting and the stresses. Of course, Fs we take it to be 0.87 Fi or some value, and then we take that. Okay. So, in this way I can find out an expression for the amount of transverse reinforcement that is required to resist that transverse tensile stress. Okay. Now, this moment is the moment that it is because of the compressive. So, the moment we are going to talk about the horizontal plane, how the internal forces are creating that moment. So, that we will explain this through an example problem. Okay. So, this is a same cross section that we have been using it throughout the course. It is a standard 500 and 200 mm thick flange with a web thickness of 150, 1 meter I section, and you can say they are pre-tension using 10 half-inch strands to 1280 megapascal, and the strands are straight with 100 mm eccentricity from bottom, and clear cover is about 50 mm. And we are taking here compressive strength of the concrete at transfer is 60 megapascal, high strength concrete, and permissible stress in the steel is 140 megapascal. Now, we need to find out what is the transmission length, and we need to find out what is the maximum transverse tensile stress going to develop in the transmission zone, and we are going to design the sections using suitable diameter of Fe 500 grade steel. Okay. Now, look at what is the gross area. We know how to calculate this, 290,000 millimeter square. Moment of inertia of cross section is, again you know how to calculate that, which works out to be 3.54 into 10 to the power of 10, and eccentricity of the pre-stressing strand is going to be 400 millimeter, and pre-stressing force you can see now 10 numbers are there, and area is 99 and effective pre-stress, this is FPE and this is area, right. So, this is AP. So, you substitute, you get the force of 1263.4 kilonewton. Now, stress at the top of the section, again P by A, and you have concentric stress component and you have a pre-stressing component also. Okay. At the top of the section, I am going to have I should say this should be compression and this should be tension. Okay. Let us say this is negative and this is plus. Okay. So, this is negative 4 point, this is 4 point. So, it is going to be plus 2.78 megapascal. Okay. Stress at the top of the section, right. Yeah. Okay. So, this is plus and this is negative in compression, right. So, you see here now stress at the bottom of the section is going to be again plus. Okay, let us say this plus and this is sorry. Okay, this is correct. So, negative 11.48 megapascal, right. So, you know the variations now. Now, what we are going to do is we are going to divide and we are going to take all the compression force of different regions and we are going to take the moment. Okay. Now, this is the CG, right. So, at this location I am having 4.35. So, basically what we are saying is, and this location you have, okay, this is about 5 millimeter. Right. So, you are dividing them into multiple regions and then we are doing the calculations. Okay. So, now what I can do is I can divide this into 2 area. Okay. So, this is one region. Okay, like this. So, this is one. So, basically this is your region 3 and this is region 4 and this is region 2 and this is region 1. Okay. So, for the region 1, if you see, it is a triangular variation. So, 2.78 at the top and the distance is 195 and the flange width is 500. So, if you substitute the entire area, I get my compression force contribution from that particular area or force contribution from that area, which is in compression, right. So, which is 135.5 kilonewton. Now, what is the centroid of this particular force? Again, using simple geometry you can calculate. So, this is at a distance of 305 because we are calculating about this CGC. Okay. Now, CGC is at a distance of 500 millimeter. Now, from the CGC this location is going to be at a distance of 435. Okay. So, that means this force for the C1 is going to be at a distance of 435. That is what it is, right. So, this case. Then you take the moment which is going to be compression and the distance is 58.9 kilonewton meter. The next region is going to be tension for a small area. Sorry, again this is also going to be in small area. So, you take that. So, that small area of the flange, it is going to be, if you see here, it is going to be half into 0.07. That is what the second area is, right, and 5 into this, and this is going to be in. Now, so the first one is going to be in tension, the second one is going to be in compression. So, the distance of this force is going to be at 301.7 millimeter. So, if you take that moment, I get a force moment of negative 0.027. For the region 3, if you look at it, because it is a trapezoidal area, we are dividing them into a rectangle and a triangle. So, rectangular force, if you calculate, stress is 0.07, the area is 300 into 150. Okay. So, 300 into 150. So, you get a force of 3.15 kilonewton and the distance of this is 150. Okay. This is only for the region 3, right. So, it is going to be at a distance of 150 and that moment contribution is negative 0.047. Similarly, we do for region 4, which is the difference, basically this is 4. So, you subtract 4.35 and 0.07. So, only this highlighted portion, the triangle, only this. Right. So, that works out to be this, and this is your thing. So, you sum all of these things and then you get your moment. So, basically we are taking the force of all the forces that are acting above the neutral axis and then taking a moment that is going to create that tension about the horizontal plane. So, that is what that moment is. Okay. So, if you do that, you get the moment of about 49.2 kilonewton meter, and the transmission length, now if you substitute it, you get about 365.4 millimeter, and beta works out to be 0.0058 as per table 1, and the maximum transverse tensile strength we already got 10 m divided by Bw2 into H into Lt, that works out to be 9 megapascal. Now, for this 9 megapascal, I need to put some steel, right. Now, the area of reinforcement required in the transmission length is 2.5 m divided by Fs into H. So, 2.5 into 49.2 into 10 to the power of 6 divided by the stress, the allowable stress is given as 140, right. So, again we put 140 times 1000, which is 878.6 millimeter square. So, that works out to be providing 9 numbers of 8 mm dia 2-legged stirrup in the entire transverse zone will help me to resist this transverse tension that are developed because of the pre-stressing. So, you can see here you put some hanger bars and so on, and the first, we need to put the first one very close to that of this region, right, and then you put 9 numbers of 8 mm dia 2-legged stirrup, and it has to be, and again this is a reinforcement specifically we are designing it for the transverse tensile stress, and this has to be in addition to the stirrup that is required for shear requirement. So, this is an extra what you put in addition to what is that is required for shear resistance. Okay. So, this is the way that we check for transverse tensile stress and also the bond length. Okay. In addition to that, there is one more provision that is given in IS 1343, and they say that for simply supported beam, half of the transmission length shall be overhang the support. That means, whatever you calculate your transfer length, this distance with the overhang over which you are going to put should be at least half of LT by 2, right. For the fixed support beam, especially when you are doing a precast and then you are embedding inside the support, then for a pretension system, they are saying that the whole transmission length shall be overhang the support. That means, this entire distance of embedment LT should be at least this much, right. You can have more than LT, but that is not a problem, but for fixed support beam at least it should go inside the support by a distance of LT. So, that because this is a cantilever kind of support, right, negative moment will develop. So, you need to develop that effective pre-stress right at the face of the support. That is the reason the code wants you to make sure that you embed the precast pretension beam at least inside by a distance of transmission length LT, right. Okay. So, let us conclude now what we have discussed in this lecture. We have in pretension member, we have discussed the basic mechanism of transferring forces to the concrete, which is through only bond, okay, and bond stress is not constant in the transmission region of the pretension member. We have seen that it is very high and then it dies down, and we have two types of bond, right. We talked about transfer bond, and then the next one is basically the flexural bond. So, in pretension members, the cracking may occur at the transmission zone if proper reinforcement is not provided. So, we need to calculate that transverse force, tension force, and then design the vertical stirrups accordingly, right. So, with that we are completing this part of the module. We will now, in the next part, we will talk about how to design the end block regions for a post tension system. Thank you.